Okay, we have been looking at 1D flows with friction, that is Fanno flow. We looked at the Fanno curve, which thermodynamically shows how these flows behave when they are starting from subsonic flow and supersonic flow. Then we looked at equations of Fanno flow, and now we will look at how these these equations and then come to the concept of what is known as frictional choking. Bear in mind, and there is it can be repeated many times because this is very an essential concept that you look at whenever you look at Fanno flows. Remember this curve. Qualitatively it looks like this. T naught is a constant, and this is the way Ts looks like. Maximum entropy point, Mach number is less than 1, Mach number is greater than 1. Here Mach number increases, pressure temperature decreases. Here Mach number decreases, pressure and temperature increases. So this is a supersonic branch, this is a subsonic branch. If this concept is known, then let us go ahead now and go towards different concepts of this friction. The first thing that we have to understand here is look at now in this it is a 1D flow, and we know that in supersonic flows one can always expect shock waves, and in a 1D flow we look at normal shocks. Now the question we can ask here is can a normal shock be present in a 1D duct with friction. Okay, so when there is a frictional flow happening, can there be a normal shock? If there is a normal shock, how will it get represented? And that can be immediately understood because one thing is shocks are discontinuity. So they do not have any specific length, or they are discontinuous. So since that is the case, and the other case is they also satisfy the equation rho 1 Bu1 equal to rho 2 V2, that means rho V equal to constant, and also they also satisfy the equation H plus V square by 2 equal to constant, that is total it is an adiabatic flow. Now how did we draw the Fanno curve? We drew the Fanno curve by just considering these two equations, and then we considered G as a parameter and rho can be varied correspondingly, whatever fits in that formed the Fanno curve. And therefore if you look at a normal shock and look at the equations that depict normal shock, they are the same. So that means normal shock, the states of normal shock can be located on a Fanno curve. So that is a very straightforward inference that you can make out of this, and this point you can also understand by the fact that there are two branches in a Fanno curve. If you take this branch, this is less than 1, and there is a corresponding supersonic branch for m greater than 1. So one can always find 2 points, right, 1 say 2 and 3 here, okay, that corresponds to a normal shock, states across a normal shock. So if you have a duct and there is the inlet is supersonic and there is a possibility of a shock occurring within the duct, then that shock can be located on the Fanno curve. So if you look at this particular problem, or this problem that is given over here, the entry Mach number is greater than 1, that is it is supersonic, then First it passes through a duct of length L1 and reaches a Mach number M2, at which there is a shock, and across the shock you get conditions M3. Okay. So, M2 conditions at 2, conditions at 3, there is no change in length because shock is a discontinuity, it is at that same location, and then you have a length L2. Now, this L2 at this particular point is having subsonic flow. So, this particular description of this problem can be represented on a Fanno curve like this. So, starting from 1, it went along this Fanno line to the point 2, the flow is still supersonic, but at this point a shock occurred, and therefore, you have this wiggly line. Of course, you cannot put any line or anything across a shock, it just jumps from point 2 to point 3. So, it is located on the same Fanno curve because G is the same. So, same Fanno curve, look at the point 3 which is across the shock. Then further there is another flow or the Fanno flow which happens for length L2. So, initially Mach number decreases in the supersonic flow, there is a shock, there is a sudden jump, Mach number becomes subsonic, then after that Mach number increases, pressure slightly decreases. So, it is possible to locate a shock in the context of supersonic flow in constant area ducts with friction or in the context of Fanno flow. And what happens actually if there is a shock, that actually we will see in a few moments. So, associated with this is the very important point of choking due to friction. So, in this context what is meant by choking? So, here if you had taken a look at the Fanno curve depicted here, you know that there is a maximum entropy point which is corresponding to Mach number equal to 1. If I take any particular, so I draw once again Ts, and this is the Fanno curve, and I take any arbitrary starting point, say this is point number 1. Okay. So, this is flow inside a duct, and let me take that at the end of the duct. Okay. So, L corresponds to L star, which is the maximum length or length of L star, where at the end of the duct Mach number equal to 1. Okay. Mach number is 1 at the end of the duct. Now, this is L star, what it corresponds to is a maximum entropy point. Now, if you look at this curve and ask the question, at this point if I increase the length by a small length delta L, what happens? Of course, this cannot be done because there is no solutions on the right hand side, and also the other fact is that an initially subsonic flow can only go up to a maximum of Mach number equal to 1, and you cannot go beyond that. So, there is a maximum length of the duct that one can give with a given friction for a particular inlet condition or for a particular inlet condition, which is L star. If one gives a length which is greater than L star, you do not have a solution in the context of this Fanno curve, something must change, otherwise that flow cannot happen. So, this fact that there is a maximum length for a given Fanno curve. Now, Fanno curve is parameterized by G, G is mass flux which is m dot by A. So, for given mass flow rate there is a, and given static conditions at the inlet, there is one particular maximum length condition. So, you cannot change this particular fact. So, how can this be changed? Then it changes if you have this particular condition that you are at L star and you want to change the length of the duct, you can do it by one case is by changing the initial conditions. You can move the initial conditions back, which is equivalent to saying that there is an increase in pressure at 1. So, if I say this is 1 prime. Okay, so, then now if I move this back, then my total length now increases. G is remaining the same in this case, that means mass flow rate is remaining same for the duct, but now I have to give higher pressure. So, that means increased pumping. So, if that is not possible, if you cannot increase pressure, then what you should what can be done is change in mass flow rate, because you can move to a different G curve, which is a different Fanno line which has lower mass flow rate. So, this is schematically represented here. So, you have a stagnation given stagnation conditions. So, that where we have a certain P1 T1 which is remaining constant. So, initially this is the initial point, started with 2 and goes to 3 here, okay, along the particular Fanno curve, along this curve, and if it goes to Mach number equal to 1 at 3, then it is the maximum length. Now, the question is, if we want to increase this length or suddenly you want to add more duct, then what will happen? Then this is not supported by these conditions. One was of course to move it to another condition located somewhere here, okay, but that is also not possible because here stagnation conditions are getting fixed over here. So, that the P naught T naught are fixed. So, that is also not going to change. Then the only change that can be done here is to vary the duct length. So, to vary the G, that is mass flow rate. So, if mass flow rate is varied, then G can change, G decreases. So, since G decreases, now you can see that the L star corresponding to this 2 prime, which is the new Fanno line at G, which is smaller prime, G prime is less than G, if G is for this and G prime is for this, then L star prime is greater than L star. So, you can add more duct. So, if you add more duct with all other conditions remaining constant, mass flow will decrease. So, the idea here is in subsonic flow, initial subsonic flow, if you have approached the choking point at the end of the duct, that is the maximum possible length that can be sustained by that particular conditions. If you want to change anything to that particular, like add more duct length, then it affects the upstream. Either you have to change the pressure, increase the pressure, thereby move along the same Fanno curve, so that you get additional length of the duct, or the other case is move to a different Fanno line, but you would see that mass flow rate decreases in the other Fanno line, which is G prime decreases. So, that is this is frictional choking. And now you see what happens if the initial flow inside is supersonic and you get a choked flow at the end of the duct, then how can you look at this particular problem? In supersonic flows, you have another medium or another solution which can help in this manner or in this matter. What is that? That is the shock. Okay. because you have this sort of condition. So, if you are already at L star and then you try to increase the duct length, then you can have shocks formed in the duct and transferring the supersonic flow to a subsonic flow, and then again you have an additional L star associated with the subsonic flow. So, for example, it is as is given here, if you take a Mach 2.18 flow, it has a value of FL star by D as 0.356. But if a normal shock were to occur at this particular point, and then the value of FL star by D after that normal shock would be 0.728. So, there is an additional length that is now possible to be accounted for, but you would of course get a normal shock inside the duct. So, in supersonic flows, if you have a choked condition, that is Mach number equal to 1 at the exit, length is maximum L star, and you try to increase the length a little bit, then it can form shocks within the duct. Okay. And amount of duct added will lead to how where the shock is located, and it can go further upstream. Okay. So, that is about the concept of frictional choking, and now we look at these influence coefficients. How these influence coefficients are derived is a matter which we discussed in the case of varying area ducts. You can write down the equations for variations of Mach number, pressure, density, temperature, express them as an equation, as a matrix equation, and then use Kramer's rule to solve them with 4f by dx by d. So, here this term 4f dx by d is the governing parameter or the driver, and that drives all these influences all these parameters. And how does it affect? This is something we discussed in detail, that when the Mach number is less than 1, initially subsonic flow, you get a increase in Mach number, increase in velocity, pressure, temperature, density decreases, and entropy will increase. F is the impulse function that decreases. Now, if you consider the case of a supersonic flow, starting with a supersonic flow, then Mach number and velocity decrease, pressure, temperature, density will increase, and entropy always increases. Okay. So, quickly let us look at a very simple problem before going on to more complex problems in the subsequent sections. So, a circular duct passes 8.25 kilogram per second of air. So, m dot is given here, m dot is 8.25 kilogram per second at an exit Mach number of 0.5. So, m2 is given 0.5. Entry pressure and temperature are 3.45 bar and 38 degree centigrade respectively, and the coefficient of friction is 0.005. So, f prime 0.005, m1 is given is 0, Mach number at entry is 0.15, P1 is 3.45 bar, and T1 is 38 degree centigrade. Okay, that is 38 degree centigrade. Okay. So, first is you determine the diameter of the duct, length of the duct, pressure and temperature at the duct exit, stagnation pressure loss. So, temperature T1 is this is equal to 311 Kelvin at 273. M dot is rho 1 A 1 V 1. So now we need to find diameter, so we need to find A. Rho 1 is given by P 1 by R T 1, and V 1 is given by A 1 multiplied by M 1, which is M 1 multiplied by square root of gamma R T 1. Okay, so you can express this. So you get A 1 is M dot divided by P 1 by R T 1 multiplied by M 1 multiplied by square root of gamma R T 1. So substitute here, this is for air. So air gamma is taken as 1.4, R is 287. Substitute these numbers here and you get 8.25, okay, divided by 0.15 multiplied by square root of gamma RT 1.4, 287, and temperature is 311, and the density turns out to be 3.865. This is 0.04025 meter square, which is, so diameter you can find out from here 22.64 centimeters. Okay, so this is the diameter of the duct. Okay, now what is the length of the duct? Length of the duct, we have the particular equation, which is L is equal to L1 star minus L2 star, or you can write this as 4FL by D is equal to 4FL star by D for 0.1 minus 4FL star by D for 0.2. Now M1 we know it is 0.15 and M2 we know it is 0.5. Therefore we just have to find this 4FL star by D. You can look at tables, or you can take a calculator, you can look at the online calculators, you can plug in these values gamma and M, and you get this as 28.334, while this is 1.069, and the difference is 4FL by D is 27.285. So from here L can be calculated, that is 27.285 multiplied by D divided by 4F. F is given, and so L will turn out to be 308.8662 meters. Okay. Now what are the pressures and temperatures? How do we get to that? So we need P2 by P1. This is nothing but P2 by P star divided by P1 by P star. Okay, and these values can be directly found out from, similarly T2 by T1 can be expressed as T2 by T star by T1 by T star, and please understand that these star values are for the Fanno curve, that is this star value is corresponding to this is the star value in a Fanno curve, and don't confuse this with star values in an isentropic flow. So they are different, but this is completely tabulated, so you can get these values. So from here if you substitute the values you can get, okay, so you P by P star at 2 is 2.138 by 7.319 multiplied by 3.45, this is 1.0086 8 bar and temperature is 1.143 by 1.1945 multiplied by 311, which is 297.59 Kelvin. So, this should be keeping with the Fanno flow that we had learnt, that initially subsonic flow Mach number is 0.15, across the duct Mach number will increase, pressure decreases, temperature decreases. So, we are good, it is in keeping with that particular equation. Now, what is about stagnation pressure loss? That stagnation pressure loss is P02 by P01, can be written as P02 star by P01 star, P02 by P0 star divided by P01 by P0 star, and from this you can get the same way that you did for P2 by P1. Now, this is in Fanno flow, okay, you have to refer to Fanno flow conditions. Get P02 is 1.196 bar and therefore, you can find out what is the delta P naught. Okay, delta P naught decreases. So, it is a decrease of pressure, stagnation pressure, which is negative 2.31 bar. Okay. So, this can be found. So, this is a very simple problem of a subsonic flow. Now, we will look at other problems in the next class. Thank you.